Hi guys, this is Mrs. Gassler, and in this video we're going to talk about the mirror equation and how to use it. And for starters, I've got this kind of blank thing that I'm going to work on filling in once I find a suitable piece of paper to cover up the other part with. There we go. Okay. Alright, so we're going to start by talking about the mirror equation. Now the mirror equation is a formula that is for spherical mirrors. And it could be used for both concave and convex, but you have to know that there's some differences there. And this is what it looks like. 1 over F equals 1 over DO plus 1 over DI. And you're probably thinking, what the heck are those? Well, F is for the focal length. DO is for the object distance. And DI is for the image distance. And conveniently, those are all distances, and so as long as you use the same unit every time, it doesn't matter what unit you use. But you wouldn't use centimeters here and meters here because that would be silly. Alright, so let's talk about what that means for concave and convex mirrors and maybe where we might put that object and image distance. Okay, so everything is measured from the mirror. I'll note that up here. Measured from the mirror. Okay, everything is measured from the mirror, but sometimes things are on one side of the mirror or the other, and so we need to know what that means. So think about it this way: if light can go that way, then it will have a positive value. Light can be on this side of the mirror, but it can't be over here, so those would have a negative value. On the convex, it's the same idea. Light can be over here, so that's positive. Light can't be over here, so that's negative. Okay, that's the way the light's going to go. Now remember, we talked about how there's a focal point, and that's where all the light rays converge. That's right here. The distance right there, notice on the concave the focal length is positive, and on the convex the focal length is negative. So that's something you want to note. Concave mirrors have a positive focal length, and convex mirrors have a negative focal length. Okay, so when you use the equation, you have to add in the positives and the negatives and think about where that means the image is. Okay, so we've got two examples. I've got two examples. I'm going to do a convex and a concave one, and I kind of picked them out to be fun here. For me, at least. I'll find them fun. You might not. Okay, so an object is placed 10 centimeters from a concave mirror with a focal length of 5 centimeters. Those are my important pieces of information there. Object is placed. That means this is my object distance. Concave means that I'm going to have a positive focal length, and this focal length is 5 centimeters. Okay, so when I use that formula, I'm going to write it down first. 1 over F equals 1 over DO plus 1 over DI. Where is the image? I'm looking for DI. Okay, so I'm going to plug my numbers in. 1 over 5. It's a positive because it's a concave. And 1 over 10. Nobody's going to put the object back here, so that's never going to be negative either. Is 1 over this image distance. Now, if you're thinking, oh crap, I hate fractions, it's okay. There's different ways that you can work this problem out. The way I like to do it is I like to find the common denominator. So this is 2/10 equals 1/10 plus something else. Oh, how convenient. 2/10 equals 1/10 plus something. This 1 over DI has to be 1/10. Do you see that? That was kind of easy. I don't know if I did that on purpose, but that's okay. 1/10 equals 1 over the image distance there. Now, since this is 1 over 10 equals 1 over the image distance, can you see that the image distance is in fact 10 centimeters? Okay. Now, if the math trips you up, do ask questions. Mrs. Gassler likes math a whole lot, and she gets it. So ask questions if you need help working through the math on these. There's plenty of different ways to do it. Okay. In example 2, now we've got a convex mirror instead. That means I'm going to have a negative focal length. I still have an object distance of 10 centimeters, and my focal length is still 5 centimeters, but this time that's a negative 5, so I'm just going to go ahead and write the negative there. So, and I'm still looking for the image, but you're going to see that because it's a convex mirror, because that mirror looks different, it doesn't do the same thing with the light. So 1 over F equals 1 over DO plus 1 over DI. And my 1 over F is 1 over negative 5. And then I've got 1 over 10. And I'm trying to find this right here. So this is going to work kind of the same way. I'm going to stick with my 2/10 because that helps me out. I seem to be running out of lead here. So I got, but this time I have negative 2/10 equals 1/10 plus something. Okay. And so, so now what I have, let's see, when I move this to the other side, I'm going to have negative 3/10 will be my image distance. Okay. Now this one is not so easy because over here I just had 1, so it was really, I could just cut those off and then it'd be the same thing. But this time I have something a little different. Now I'm a big fan of cross multiply. Maybe you'd rather just do the inverse of that. It's totally up to you. But what I'm going to end up with is my image distance is 10/3. 10/3. I don't even know how much that is. But I got this handy calculator. It can tell me 10/3 is 3.33. Now remember, that's negative. That means that I have negative 3.3 centimeters. That means that my image is, so if I started out with 10 centimeters over here, maybe that's like here, then my image is at 3.3 centimeters. So it's inside that focal length because the focal length was 5, and that's where my image is going to be. So that's how you do the mirror equation. Now there's a couple of other things that we can do with this too, and I don't remember if they're in your practice or not, but you can talk about whether or not it's magnified by thinking about the magnification, which is going to be the image distance over the object distance. Okay, so if we put the image distance on top and the object distance on bottom, then we can that ratio will tell you just how much bigger or how much smaller the object is. That's the magnification, and it's just a multiplier. That's something else that they like to look at. If you don't have the image object or the distances, this is the same as the height of the object over the height of the image. Sometimes a question might tell you the magnification and ask you how big something is going to be, or maybe you can figure this to find the magnification and figure out how big something is going to be, but that's just an extra formula there. Okay, so thanks for watching. If you have any questions, make sure you let me know. Bye.